In this example, what we're going to be looking at is we're going to convert eventually moles of gas, starting with percentages, into numbers of gas molecules. So let's read the question. A sample of air contains 78.05% nitrogen, 20.94% oxygen, 93% argon, and 0.05% carbon dioxide. Now the rest of it will be a bunch of different, will be some water, sulfur dioxide, NOxes. All right, but so this doesn't entirely match up to exactly 100%. It's off by just a little bit, by 3/100ths. But that's because the rest of it will make up sulfur dioxide, water, some other things such as that. And so how many molecules of each gas are present in 1 liter sample at 25 degrees Celsius and a pressure of 1 atmosphere? So the volume is going to be equal to 1 liter and the pressure is equal to 1 atmosphere. Now, if it's 1 atmosphere, if that's the total pressure, then what this means is that the pressure of the nitrogen is going to be 0.7805 atmospheres. That's going to be the pressure. Likewise with the oxygen, if 20.94% of the 1 atmosphere is due to the oxygen, then the pressure is 0.2094 atmospheres of oxygen. This is nitrogen. Likewise, argon is going to be 0.0093 atmospheres of argon. I'm just simply converting the percentages to decimals. And this will be equal to 5 times 10 to the minus 4th of an atmosphere of carbon dioxide. Now, in order to determine the number of moles, right, to use the number of moles, we're going to use N is equal to PV upon RT. Now our temperature here is going to be 298.15 Kelvin. And what we're going to do now is we have the pressure, so you simply plug in the pressure. So I'll do the nitrogen for you. So if we do the pressure for nitrogen, that's going to be 0.7805 atmospheres times the volume, which is 1 liter, divided by R, which is 0.08206. I'll make a little bit better parenthesis. Oh, that's a little bit better, not much. Liter, atmosphere, mole, Kelvin times our temperature, which is 298.15 Kelvin. We do that arithmetic, and this will give us 0.032 moles of nitrogen. Now we continue to put, so instead, for oxygen, what we do is we would put the pressure for the oxygen in for here. And we do that arithmetic, so everything else will stay the same because it's still going to be 1 liter, still R, and still at 298.15 Kelvin. But you would plug, this is going to be your pressure, you would plug your pressure in for those. And so by looking at the oxygen, you get 5.15 times 10. Oops, I got ahead of myself. Nope, it's not that. Oop, read the wrong number, sorry. This is going to be 8.559 times 10 to the minus 3 moles of oxygen. The argon one is going to be 3.801 times 10 to the minus 4 moles of argon. And the carbon dioxide is going to be 2.04 times 10 to the negative 5th moles of CO2. Now, if we want to get this into molecules, what we do is we then multiply it by 6.022 times 10 to the 23rd, and this is going to be this will be atoms or molecules per mole. And so if we do that arithmetic, what we end up getting is we get 1.93 times 10 to the 22nd nitrogen molecules. Once again, we multiply this by Avogadro's number, and we get 5.15 times 10 to the 21st oxygen molecules. We do this for argon. We multiply this number by Avogadro's number, and what we'll end up getting is we'll get 2.29 times 10 to the 20th argon molecules. And then if we do it for CO2, we'll take this number and we'll multiply it by Avogadro's number as well, and we get 1.23 times 10 to the 19th CO2 molecules. And so if we have a liter of air, and it happens to be at 1 atmosphere, and the volume is 1 liter, and the temperature is room temperature, about 25 degrees Celsius or 298.15 Kelvin, these are going to be the number of nitrogen molecules, oxygen molecules, argon atoms, and carbon dioxide molecules. If you have any questions on this, on partial pressures, on stoichiometry, and stoichiometry is mostly unit conversions pertaining to gases, please let me know so I can help you.